Hello everyone, welcome back. Let's talk about another medium problem on Leetcode today. Linked list in binary tree, Leetcode 1367. In this problem, we are given a binary tree root and a linked list with head as the first node. Then we should return true if all the elements in the linked list starting from the head correspond to some downward path connected in the binary tree, otherwise return false. In this context, downward path means a path that starts at some node and then goes downwards. Then in example 1, in the given binary tree, there is a downward path that matches a linked list with values 4, 2, and 8. The path starts with one of the nodes with value 4 and then goes down to 2 and then reaches 8. These nodes form a subpath in the binary tree matching the linked list, so we return true. Similarly, in example 2, in a given binary tree, there is a downward path that matches the linked list with values 1, 4, 2, and 6. The path starts from the root node with value 1, goes down to 4, then to 2, and finally reaches 6. These nodes form a subpath in the binary tree, and we again return true. So the linked list can either start from the root of the tree or from any node within the tree, making it essential to check all possible starting points. So now what is a naive or brute force way of solving this problem? Well, we can start by traversing the binary tree from the root of the binary tree and then trying to find any node that matches the head of the linked list. In general, many tree problems involve traversals and we solve them using depth first search or DFS. So let's take example 1 to come up with our approach. So we start with the root node and we see that value 1 don't match the head of the linked list, that is 4. So now we move to its children. So we go to the left and right, and let's focus on the left side first and then we will go to the right side. And now we find that the left child of the root, that is 4, matches the head of the linked list. And then we will recursively check the left and right children of the current tree node to see if they continue to match the subsequent nodes in the linked list. So because we have now matched 4, we still need to match remaining linked list nodes 2 and 8 in the binary tree. And if at any point the values of the linked list node and the tree node do not match, or if we reach the end of the tree path, this means that there are nodes remaining in the linked list and we couldn't find the complete linked list in the binary tree, so we will backtrack. Now let's continue with our example. Now because the tree node value and the head node value matched, we will do head is equal to head dot next. So we will come to 2 now. Then we further explore the children of 4. We come to 2, right? And that also matches the current head value, that is 2. So we come to next node in linked list, that is 8. Now we again explore the children of 2 and only child it has is 1. And that doesn't match 8. So we will now backtrack. And now we again come to the root node. We have not explored the right side yet. So now we come to node 4. And when we backtrack, the head is again pointing to 4. And we again see that the head value and the node value matches. So this is again our potential starting point. So we will do head is equal to head dot next, right? So we again come to 2. So we explore the children of node 4. We see that there is only left child and the value of left child is 2 and the value actually matches. So we will again do head is equal to head dot next and we will also explore the children of 2. There is only one right child, that is 8. We see that the value in the linked list, that is 8, and the current node actually matches. So we will again do head is equal to head dot next, and now we have come to the end of the linked list. So that means we have successfully found the linked list as subpath in the binary tree, and that means we should return true. And note that successful ending condition for us is that we should reach the end of the linked list even though there may be some values remaining in the tree path, because we want the complete linked list in the binary tree. So that's how this whole approach will work. And even though this looks like a naive approach, this is still quite efficient because by starting the DFS from every node in the binary tree, we ensure that no potential starting point of the linked list is missed. And whenever we find out that the value in the linked list does not match with the value of the node in the binary tree, then we backtrack, right? And in terms of time complexity, it will be O of m into n, where m is the length of the list and n is number of nodes in the binary tree. And the reason is the DFS traverses each node in the binary tree, and for each node, it may check up to m nodes in the linked list. Therefore, the time complexity is O of m into n. And in terms of space complexity, it will be O of n, mainly driven by the recursion stack, and it will be equal to the height of the binary tree. And in the worst case, height of the binary tree can be equal to n. So that's why the space complexity is O of n. Now let's jump into the code part. So first thing we will check is if head is null, then we should return true. because an empty list matches any path. Now we check if root is equal to null. So that means linked list is not empty, but tree is. So it can't correspond to any path. Hence we return false. And now we will start our DFS to check if the current binary tree node and the current linked list node matches, and subsequently if their children continue to match or not. So we'll pass in head and root for that, and it will return a Boolean value. But if we couldn't find a linked list starting at the current root node, we will recursively check the left and right subtrees to ensure all possible starting points in the tree are covered. So we will do is subpath. We'll pass in the head value and root dot left. And if it couldn't find the subpath on the left, we will try to find the subpath on the right. This is what this OR operator does, because if this value returns false, then it will go to this one. And if this value also returns false, it will go to the end. And if all the values are false, it will return false in the end. So now let's write our DFS function. So we will pass in the same two values, list node and tree node. And we will again need these two conditions. So again, the same condition applies. If head is null, that means we have reached the end of the linked list. So it matches till the end, and hence we return true. And similarly, if we have come to the end of some path in the binary tree, we will return false because there are still some values remaining in the linked list and we have not completely traversed it. And once we are here, we will check if the root value matches the head value. And if it does, we continue to check both left and right children of the current tree node with the next node in the linked list. So we will just do DFS of head.next and root.left child, or DFS of head.next or root.right child. And that's it. Now let's run this code. Cool, let's submit this code. Awesome. And just a minor thing, we don't need to check if head is equal to null here in its subpath method, because we are anyways checking it in the DFS as well. But the null check on the root is required because we are doing root is equal to root.left and root is equal to root.right here. So because of this, we may get null pointer exceptions. So maybe I can get rid of this, and let's run this code again. Let's submit it. Cool. Time complexity stays the same. And I hope this video was useful to you. If it was, please like, share, and subscribe. The code link is in the description below. If you have any questions or suggestions, please write it in the comment box. Thanks for watching. Have a nice time.